All right, and now we are ready for example 1 right here. So our example 1 is asking that we want to approximate the solution of the equation x to the 4th minus 4x cubed plus 1 equals 0 with starting point at x sub 0 equals about 4. Okay, and so that's the problem that we're having at start. So now getting into it, and like I said earlier, the intention of these problems are not the intention of these problems, or for viewers and for students of mine, or to be able to find the approximates without relying too much on the graphing calculator. Okay, so if you use a graphing calculator, the most it can tell you is to know that what to expect, that we're gonna expect a solution. But then in the end, the graphing calculator is not able to help you to approximate, and that's why we're now gonna come up with this actual. We're gonna rely to this actual Newton's method right here. So now I have a given point. So the good thing about this example problem is that we are given already by, maybe it could be me, it could be some instructor who has already been experienced and who and giving out, and that's how it happens with a lot of time in these problems for the students at the beginning level of calculus, learning the Newton's method. Then usually in your problem you are suggested with a starting point right here. So there's your equation, and you're being suggested at this starting point, x sub 0 equals 4 here, and let's approximate the solution of this. So before I do any further work through here, so now what we recognize is f of x is x to the 4th minus 4x cubed plus 1. Let's take a quick pause here, because here's the thing. Now all of a sudden we realize this function that we recognize right from the equation, and yes, the equation already had all the non-zero terms to one side, and the opposite side is a 0, and that's the critical requirement right there. And so now we can recognize our function here being x to the 4th minus 4x cubed plus 1. But then, isn't this function here the exact same function that we have done throughout the introductory problem where I promoted the idea of using Newton's methods? Yes, it is, because now I actually designed this example in a purpose for my viewers and my students to understand that. So let me bring up the graph here, and we will all understand together. But the actual graph of this function x to the 4th plus minus 4x cubed plus 1 is not only crossing the x-axis at one point. We were attempting to find an approximate for this solution earlier throughout our introduction problem. But now, indeed, this graph has another 0 out there. It's right here, okay? It has another 0. And that's why, you see, being already experienced, I chose this x equals 4 for my students to be the start. And then my students can just, or any viewer, see, think about if you're putting yourself as a student doing this problem from a teacher, from a professor, then, the professor will suggest a starting point, and you will go ahead and do the steps of calculations with that. Okay, and so now back on the problem. So you can see that I used the graph to show that x equals 4 is not yet, right, the actual value, but the actual value is already pretty close. The actual value of our solution is actually pretty close to 4, but 4 is not the actual value yet. Okay, and so let's see how we can do the calculation. So now I'm going to switch back to my board, and we're going to be entirely using the formula. So the first big step, we need the derivative. And that's why this study here is all about we applying our ability in taking derivative into our work. Our derivative for this function is 4x cubed minus 12x squared. And I don't need to worry about anything about factoring out or anything like that, or even simplifying our derivative. That's not the important part. Okay, but now we can see that we have a start, or maybe let me write it on the other board right there. We got a much more space there available there. So here's our start. Our start is at x sub 0 equals 4. Okay, and so that means my x1 here, the next step to get to, and you have also seen that on the graphs. And the later problems, I won't show the graph anymore. We're just gonna take the start point and move on. Okay, but so x1 here is supposedly closer to where you saw it on the graph, to where the graph crossed the x-axis. And so now x1 here is going to be, according to the Newton's method formula, then it's x sub 0. If this is n plus 1 here, then x sub n is this one. So x sub 0 minus f of x sub 0 over f prime at x sub 0. And then here the value is short enough so that I can easily quickly write it down right here. It's 4 minus f at 4 divided by f prime at 4. Okay, so my calculation, allow me a minute or so to step out for calculation. All right, so my calculation showed x1 equals 3.983475. Let me quickly double check before we move on. I actually had it written backward there. And then viewers who are doing this independently with me can also double check for me. 984,375, that's what it is. Okay, and so now that's our x1 value. And so once we've had x1, let's go ahead and record that. So now we already knew that x sub 0 is equals 4, that's our start. So now I'm going to erase that and write all of these here as a recording of our work here. X sub 0 is 4, and we came down to x1 being 3.984375. Let's now head out for the x2. Okay, so x2 here, just like that, we need the formula, and I don't need to take away my board space. Let's just do it right here with some small modification. So x2 is here. That means I need x1, the preceding step right here, minus f of x1 over f prime of x1. Okay, that's what the formula is. So the formula is applied to every single step right there. So now 3.984375, subtract the function value at 3.984375 divided by f prime at 3.984375. Okay, and so again, allow me to quickly step out or step away for a calculation, and I will be back. All right, so my x2 value is 3.984188, and 25768. Okay. All right, so this is our x2, and it could be a lot longer, but unfortunately my calculator only showed this, and I have to apologize for keep swinging back and forth because it's such a lengthy decimal calculation right there. Okay, so now that's x2, and you can see that it's already closer, a lot closer to, it came closer to the value we need. So x2 here is now on record, writing that into our recordings, 3.984, okay, 188, 25768, and a lot longer. Okay, and that's our x2. And so now let's look at x3 right here. All right, so x3 is found by, once again, I'm going to look at x2, I'm going to subtract the function value at x2, and I'm going to divide it by the derivative at x2. Okay, and just like the formula just like the formula being written down for the Newton's method, and that's here we're applying that here. And so all that x2 is here, and which is now pretty lengthy to write, so I'm not sure if I can write all of that there, but so 3.98 4188, and a lot longer. How's that? And so it's not really a rounded version. It just I had to leave the remaining decimals out to leave myself enough space. Minus f at 3.984188, okay, and a lot longer, divided by f prime at 3.984188, okay, and a lot longer. And so now again, I am going to step away momentarily for another calculation of mine. All right, so now I have come to 3.984188, 23121, and a lot longer. Okay, and so that's my x3 right there to be written down. That's my x3, and so now I'm going to record that. x3 is 3.984188, 23121. Okay, and notice how my x3 and x2 are agree up to 2, 4, and 6 decimals or 8, and it only start actually 7 decimals, and it starts departing. It start being off after that only at the last 4 digits right here. Here's a 5, 7, 6, 8 for my x2, and here's a 3121 like that. Okay, so the x2 and x3 already agree with each other up to the 7 decimal places. Okay, and then look at x1 and x2 right here. These two answers agree up to 3 decimal places, right? So it only agree up to 3 decimal places between x2 and x1. But after that, all of a sudden, x2 and x3 agrees up to 7 decimal places. So of course, we can keep going if we're still unsatisfied with any of these on record right here. So we can go with x4, and we can go with x5, and we can go with x6. And this is now the first the detail that I want to mention now, that I was not able, that I didn't want to bring it out too soon yet. But so now, how far do we go? How far should we go? Are we going to just stay at, so this is the starting point, and of course it's not, so this is the starting point, okay? And that's the first step away, so of course starting point usually being quite off from the actual solution. But then x1, are we going to stop at the value that x1 came out because it's close enough? Or are we going to stop at x2? Or we are going to stop at x3? Or we need to go further? So how far do we go? That's the first detail that I did not bring it out earlier when I was introducing the kind of problem here, the kind of method. So here's the thing. Let me now go back and add in this line right here to our beginning problem. I mean to this particular problem in our example. So how about, so we want to approximate the solution, right, of this equation here with the starting point. So we know we have a starting point here, and let me erase this work here that's no longer needed, okay? But how about, I'm going to say accurate, okay, to about 6 decimal places. Okay, so if the problem from beginning to the end, being precisely worded like this, then accurate to 6 decimal places. Now we have an instruction telling us how far we should go in terms of how many steps we should go so that we can meet the 6 decimals accuracy, 6 decimal places accuracy. And so here's the thing. the rule for this, the good rule of thumb for this. So we want 6 decimal places accuracy. So that means, think about it. Any of these 2 steps, think about x of 0 and x1 right here. Do these 2 steps right here agree up to 6 decimal places? No. This is 4. This is 3.98. It's already off right by the first decimal. So we don't want to. So we don't want to stop here. We want to go further. Okay. And so now we're going to look at x1 and x2. Basically, we're going to keep looking at pairs, at different pair of consecutive 2 steps right here. So x1, its consecutive one is x2. Okay. So looking at these 2 pairs, they only agree up to 3 decimal places. x2 and x3 only agree up to 3 decimal places, and after that, things are gonna depart. Okay, and so we don't want to stop at any of these answers here. So now we look at x2 and x3 here. Okay, now we're looking at x2 and x3. So here's the thing. Yes, these 2, they do agree within the. So x2 is 3.984188, okay, 2, 4, 6 decimal, and even a 7th one. So x3 is 3.9841882. So x2 and x3 actually agrees within 7 decimals. 7 decimals. So that means we only need our answers. So that's one thing I pointed out. x2 and x3 already agree up to 7 decimals. But then we only need our answer to be accurate to 6 decimal places. So this is how we're concluding our answer. The answer here is not really about x2 or x3, but the answer is whichever the answer that's meets with our rounding requirements. So up to 6 decimal places of accuracy, then our final answer here is the solution. Now I'm not going to say x2, x3. The solution to the equation is about 3.984188. Okay, 6 decimals. Okay, this is something that both of my x2 and x3 can. So basically, we keep checking for our. So think about on your work right here. If you only gone by far from x0 to x1, and your work did not agree up to the number of decimals yet, then we have to get further. So x1 and x2, if you're currently there, and your x0 with x1 do not agree within that, then we have to go to x1 and x2. That means you go further. And then x1 and x2, if still does not meet this requirement, then you're going to go to x2 and x3. And as long as x2 and x3 meet with that requirement, then we're going to pick the answer. Not really the x2 or x3 or whatever, but we pick the answer that meets 6 decimal places requirements, that the two later steps agree with each other. And so now the reason I choose 3.984188, because within 6 decimals, x2 and x3 agree with each other, and my 2 later steps. So that means further that I no longer have to go for x4, okay, because the problem here only requires 6 decimal places. Okay, and so that is how we are solving for this problem right here. And so before I close down the example and move on to another one, let me now also point out a few other things, a few other details that we won't be able to cover that in this class right here. But if any of you have a good passion for this kind of method, this style of solving an equation using numerical methods, then you're going to need to advance to a higher course or more advanced course. But there's an entire world about how to pick a good starting point. So if you're a student studying with me, then most of the time I will suggest throughout problems for you to exercise, for you to practice. Then I will provide a starting point. I'm not saying that you can't do that on yourself, on your own, but you need more experience. You need more experience to pick a good starting point, otherwise it's gonna fail. There will be a certain place. I will briefly talk about that at the end of our video lesson here. But there will, if we're not experienced and pick a starting point, some starting point, then it could fail. Okay, some starting point can lead to a failing work right here, and so that's why, like I said, if you're a student of mine studying with me, then I will suggest a starting point like right here in this example. And I also believe that if you're just general public viewers out there, and of course you're learning this because you're taking courses somewhere here and there with your own professors. Your professors should also be the one that's more experienced and will give you a suggestion of what value to start out. And most of the time your job is just to go through the sequences of steps right there and to calculate the steps and to get closer until you reach this decimal requirements of how precise, how accurate your answer should be. And so because like I said, at beginning calculus level here, that's all the expectation is. The students are only expected to understand how to carry out the methods, but these other details. So at some courses where you are trained enough, at some advanced course where you are trained enough with all the differentiability and all the skill in differentiation, then you should be able to pick your own good starting point like that. Okay, and but at this level, usually teacher would need to give a suggestions or even the problem being assigned like that. Somewhere here and there in the problem, there has to be a suggested starting point, and students are just gonna take that starting point and carry on with the rest of the method like that. Okay, so that's another detail that I really have to leave that for you, if you for anyone viewing this video, that if you have a good passion for this kind of methods right here, then you're gonna have to take a higher course in math, and there you will learn technique how you can choose your own good starting point to make things to guarantee you will land into a solution. Okay, so now let's get into example 2 right here. So it seems like I've been leading anyone into the impression that this method is for solving equation. Yes, it is primarily for solving an equation, but now let me even apply that into a slightly different context, and then I'll be able to make the connection, make the bridge between the two right here. But how about I'm now going to use the Newton's method to approximate a value, a numerical value, square root of 2. See, I mean, up until this point, trust me, anyone viewing this video, provided that you've learned this video, that you really are just a beginning calculus student, and if I'm asking you to find the value of square root of 2, your only choice is to rush out a calculator, punch it in with a square root. But think about how the programmers to those calculators program the value for square root of 2. How can we get something like that? So this is about, you pretend that your job here is to be those leading programmers who make the calculator give the answer for square root of 2. Otherwise, we're permanently stuck with this we call precise expression. But in real decimals, we don't know what that value is. Okay, so this method, this Newton method here, helps us to find that it's actually a good place for us to do this work right here. We want to now approximate the square root of 2, the actual value of square root of 2 in decimals and all that. Okay, so approximate square root of 2, and how about, now I'm going to say accurate. Okay, accurate to right, 6 decimal places. And starting at x equals how about 2. Okay, starting at x equals 2. Now, see, you can see that definitely square root of 2 is not equal to 2. Okay, but I'm saying that let's suggest that x started at x equals 2. But so now, before we really get started into that, how do I see a Newton's method can be applied in a problem like this? Because here's the thing. First of all, I thought the instructor here has been giving viewers the impression that the Newton's method is for approximating the solution of an equation. So where's the equation here? This is a value to find. This is a value to approximate. So where is that equation? So the truth here is this. Think about this. If we're calling that value, if we're attempting, let me go back and modify that as x sub 0. How's that? Because I want to use the x for the actual value here. If we are trying to really find the value of square root of 2, x equals square root 2. That's on standard how we find that. That means it came out from x squared equals 2. Agree with me or not? Okay, pause the video, take a moment to think about it. Squaring both sides right here, that gives me x squared equals 2. So really, the value x equals square root 2 came out from solving this equation x squared equals 2. Or in other words, subtracting 2 from both sides, x squared minus 2 equals 0. So this value right here, square root 2, really indeed came out from an equation x squared minus 2 equals 0. It's a quadratic. And yes, even though using the quadratic formula or complete the square method or whatsoever, we are going to end up with imprecise, inexact solutions. Then it's square root 2. But now we in a need of looking for decimal expansion of that. Then how are we going to get that value here? And by the way, an equation like this, for sure you have learned by heart. You know by heart that it should end up with, this equation end up with plus and minus square root 2. So my intention here is to only approximate this value, okay? And of course, it's nothing contradicting with what you've learned. It's just instead of aiming at the negative one, I'm only aiming at finding the actual numerical, the value, the numerical approximation of square root of 2, okay? And when you are experienced enough on your own, you can also approximate a value for negative square root of 2, okay? And so now with this problem, I don't need to bring up the graph at all. So just like how I was working it through here briefly and already erased that, then square root of 2 is really the root of x squared minus 2 equals 0. So that, in other words, this work here is the same as approximating the solution, the positive solution of this equation, okay? And this equation, once I now have successfully put that in a form of all the non-zero terms on one side and 0 on the opposite side, then now we can recognize that f of x is x squared minus 2. Okay, and your f prime of x will be simply or easily 2x. See, you got to apply some of your calculus understanding, taking the derivative. Okay, and so now once you've got your derivative and you got your function here identified, your beginning function identified, and your ultimate equation that you're trying to approximate, the root is here. So now, like I said, allow me to assume that students viewing this video, either students of mine or just public viewers out there, allow me to assume that you're at the very beginning level. So when you're without too much experience yet, right? Because you're beginning into this, and so allow me to suggest a starting point. So I suggest let's start out with x sub 0 equals 2. Okay, so now I am going to get on the other board and let's do the calculation here. All right, so on my other board, yes, the start is already suggested or given. So we simply just going to take that and move on to the next step. So the Newton's method formula says to find x1, which is supposedly closer to the actual value of square root of 2. Okay, then we're going to go x of 0 minus f of x 0 over f prime at x of 0. Okay, so it never hurts to just copy down the actual formula at every single step. Okay, just to remind yourself what you can do, because sometimes it has a lot of work involved with that. So writing it down gives you a sense about laying things down and making it easier for yourself. So x of 0 is 2. So now we're looking at 2 minus now f at 2 divided by f prime at 2. Okay, and so now that gives me, so it is going to be 2 minus now f of 2 is going to be 2 over 4, which is 1/2 here. So now I jump down to, so x1 is really 1.5. Okay, because 2 minus a 1/2 here is going to give me a 1.5. Okay, so that's my x1 right here. So let's go ahead and write it on records. Write it down into a recording of our steps right here. So x1 equals 1.5. Okay, and so now after getting to this, then x1 right here, then we're going to move on to x equals, let's move on to x2 right here. All right, so x2 is going to be found by the exact same formula. X1 minus f of x1 divided by f prime of x1. Okay, and so my next step here is going to be just substituting in the value 1.5 minus f at 1.5 divided by f prime at 1.5. Okay, and at this point right here, decimal is starting to get pretty lengthy. Starting to get long already, so I'm going to step away for a quick calculation on my screen right here. All right, so x2 of mine, after going through all that calculation, is going to give me 1.41666666, and all of that, the infinite sequence of 6 right there. Okay, so that's my x2. All right, so x2 equals 1.416, all the repeating 6. So let's double check. So we are currently at x2. And the problem wanted us to keep going until we reach 6 decimal places accuracy. So let's see if we've gotten that yet. And so in this way, so far I've had x2. And x1 was only 1.5. So these two answers already differ right from the first decimal right here. So that means we have to go further, because it's not even anywhere close to agreeing within 6 decimal places. So now we have to go further. So that means I'm going to need to look for x3. But so now for this particular problem example right here, every step that we found, I will go ahead and find an actual check, okay, to make sure that we already land at our destination right there. But now since x2 didn't reach our need right there, so now I just simply recorded it. But I'm now going to go ahead and move on to my x3 value. So x3 is the same as x2 minus equal value with x2 minus f of x2 over f prime at x2. Okay, and so now that means we're looking at 1.41, and with all the repeating 6 right there, minus f at 1.41 with the repeating 6 divided by f prime at 1.41 with all the repeating 6 right there. Okay, so that's our value. That's the calculation setup for our x3 value. So let's look at x3 right here. I am going to again step away from my from my board for a quick calculation. All right, so calculation of mine show 1.4142, okay, 1568627, and a lot longer. So that's for my x3 value. So once again, let's double check right here. Let's check between x2 and x3 to see if we should stop or we got to move on further. So x3 is here. x2 is 1.41 with all the repeating 6. So x3 and x2 already agree up to 2 decimals. Okay? But that still doesn't look like the requirements that we need yet. Still just only agreeing within 2 decimals. So that means I'm going to go ahead and record this value and move on to the next one. So now I need more board space here. So to write my x3. So x3, record it down as 1.41421568 okay, and a lot longer. And now I'm going to go ahead and calculate x4. All right, so x4 here is going to be, I'm going to need x3 minus f of x3 over f prime of x3. Okay, and so now that means we're looking at 1.4142 and a lot longer. Allow me to chop off all of those. It's not really a rounding. Again, it's just I have to hide away all of those other digits right there because I'm short of board space. And then f at 1.4142 and a lot longer. and then f prime of 1.4142 and a lot longer. Okay, so that's another value that's another setup waiting for a calculation value. All right, so calculation of mine shows x4 is to be equal to 1.4142 1356237. Okay, and a lot longer, of course. All right, but and this time here, let's check to find out whether we need to proceed further. And so x4 and x3 previously written down right here, recorded down right here, the two steps now agree up to within 5 decimals. But that's not enough. We need 6 decimal accuracy. So that means I'm going to need to go further. I'm going to have to head out for x5. So now before heading out to x5, I'm going to go ahead and record down my x4 here. Okay. So x4 came down to be 1.4142 1356237. Okay, and a lot longer. All right, so now x5 is ready on its way. So x5 here is 1.414 to 356 56237 and a lot longer, but I don't think I need all of those. So now at this point, let me make another clarification. When you're actually using your calculator, make sure you maintain the full precision, don't round and then use that for the next value, because it's gonna start leading to some off of the decimals. Okay? So when you're still part of the calculation and when you did not reach your final answer, don't round any of these yet. Okay, and so now x5 is x4 minus f at 1.414 to 1.356 and a lot longer. So instead of writing down the formula here, I'll just get straight into the formula with the value of x4 substituted in. So f prime at 1.4142 1.356 and a lot longer. Okay, so now x5 okay, so now my calculation shows 1.4142 1.35 6237 and a lot longer, of course. Okay, but now let's look at x5 and x4 together to double check whether we have reached the requirements so that we don't have to move on. So x5 and x4, they agree up to almost all of those. So let's see how many digits here. 2, 4, 6, 8, 10, and 11. So x5 and x4, I don't know what else. Even my calculator didn't show anything else further than those, but x5 and x4 agree up to agree up to like 11 decimal places. So now that means we have come to our, so that now rings a good sign, a good bell that we don't have to move on to x6. With x5 here, it's good, but I'm not saying that this is the final answer. It's just we're going to pick the answers because x5 and x4 already agree up to 11 digits, 11 decimal places. So we only need to pick the 6 decimal places here, okay, and round properly. Okay, so that means our final answer now, the actual solution now is going to be, okay, in 6 decimals, 1.41421 3, okay, 2, 4, and 6. So that means I am going to round this to 4. Okay, if we just round. All right, but that's the answer of our problem here, accurate to 6 decimals. That's our solution of this equation here, accurate to 6 decimals. All right, so the last one, I just want to show another example. Right, so example 3, let's now approximate the solution of cosine of x equals x. Okay. Accurate to 6 decimals. Okay. With starting point, allow me to just write it for short, start point at x equals x of 0 equals 1. All right, so x of 0 equals 1. That's our starting point. Okay, so now our equation, cosine of x equals x. Okay, so this equation here is not quite in the ordinary form, because ordinary form I need all the non-zero terms to be on one side, and then leaving the opposite side a 0. So I'm going to simply subtract both sides by x right here. I mean, subtract x from both sides. So we're looking at cosine of x minus x equals 0. And so there I am now going to easily recognize my f of x to be cosine of x minus x. And that will consequently lead down to my f prime has to be minus sine of x minus 1. Okay, so that's the two essential keys that we need right there. All right, so now I'm going to take some time erasing the other board, and we're going to navigate over to the other board for our actual work right here. And so with x of 0 equals 1, I am now going to calculate x1 to be 1 minus f at 1. So viewers at this point have seen really 3 examples, 3 problems how the same methods being done. So allow me to skip writing down the actual formula. I'm just going to write down the setup, but with the value substituted in. So how about f1 over f of 1 minus f over f prime of 1 here. Okay, and now I am again going to step away for a little calculation here. All right, so my value here for x1 is going to be 0.7503 6386 784, and a lot longer, of course. And let me double check with what I wrote down on my notes here. All right, so that's value right there. And of course, we shouldn't stop here, because the problem was asking for accuracy up to 6 decimal places. Okay, 6 decimal places, but so far we're still off, quite off, because with our answer being 0.75, and with x of 0, I mean for x1 it's 0.75 some, and x of 0 is just 1. So we're still quite having some disagreements between x1 and x0. So that means let's move on. Okay, but now before moving on, I am going to record down. And so x of 1 here equals 0.75036386 and lots longer. Okay, and now ready for some further action. So that means now I am going to find x2. And so with the same formula being repeated here, x2 is going to be Okay, x1 minus f of x1 over f prime of x1. And so 0.75036 and a lot longer. Subtract and allow me again. This is not a rounding. It's just I did not display the remaining of the decimals. Minus f of 0.75036 and a lot longer divided by f prime at 0.75036 and a lot longer. Okay, and so now again I'm going to quickly step out for another calculation right there. All right, so calculation came out showing that my x2 equals a 0.7391128 90911. Okay, and a lot longer. Okay, so again, let's double check to see whether we have met our requirement. So this x2 and our x1 here, they only agree up to 1 decimal. So that's not quite meeting the requirements yet, but at least we're starting to have some answers that some steps that agree some certain decimals. So let's move on. Okay, so now I'm simply gonna just record my x2 value. So x2 here being recorded as 0.7391128909111 and a lot longer. But now I'm gonna proceed to calculating x3. All right, so same setup right here, but I'm going to use x2 as for my substitute it into my formula. So 0.73911, okay, and a lot longer, of course. I just didn't display. It's not a rounding, so don't round these value that you're substituting and take the exact value. Your calculator should be strong enough to just copy and paste the preceding answer right into the next step calculation. So here I'm just chopping off, not because I rounded, just because I couldn't display all the digits there. Minus f of 0.73911 and a lot longer divided by f prime at 0.73911 and a lot longer. Okay, and so now again I'm gonna quickly step away to find out what my calculation value is. And actually now this time, just one time stepping away, I am going to do the 2 calculations in case we need a further one, so that I can reduce my time back and forth right there. All right, so my x3 value came out being x3 came out. The actual value now being 0.73908, right? 5133385. And that's my x3 like that. And so now, once again, let's check to see if we can stop here or need to go further. So this answer x3, this x3 compare with our x2, we already have some agreement up to 3 decimals. Okay. So 0.739 and here's 0.739 agree, the 2 steps here agree up to 3 decimals. Meaning we didn't meet it yet. We didn't meet 6 decimals requirement, so we need to go further. So now I'm going to simply just record x3. So x3 here is recorded down as 0.73908513338 and a lot longer, of course. But now I am going to proceed into calculating x4. So x4 should be now using the, and like I said, do not round any of these steps if you're using that for the next calculation. So 0.73908 and a lot longer. I'm going to subtract f at 0.73908 divided by f prime at 0.73908. Okay, and so now, so my calculation that I looked at the 2 calculations. And so x4 he actually came out being 0.73908 5133215. All right, and a lot longer, of course. Okay, and now let's look at our x4 and our x3 here. The answers, the two answers agree up to that many decimal places. Okay, so look at what I underlined so far. Look at what I underlined. Okay, and so from x3 that we already put that in our recording work, and then this is x4. We just now found right here the answers agree up to 2, 4, 6, 8, and 9 digits, 9 decimal places. So now it rings a good bell that now we can stop right here. So we don't need x5. We stop at x4 right here. But now what's our final answer? So what can be concluded as our final answer? The final answer only requires 6 decimal places accuracy. And so that means my actual solution to this equation is going to be x is approximately equal to 73985. Okay, and rounding properly, it lands right into 5. And so that's how we are doing that. Okay. All right, and so before we're completely done and move out from this lesson right here, so back to what I said earlier, what did I mean by sometimes the starting point can be a failing one, or in other words, sometimes the method can fail if we happen to choose a starting point that doesn't work. And so after the video lesson, and of course, and if any of the students here, if any of you, the public viewers, have done all of your assignments with your professors, provided a starting point, I also recommend outside of your study time with the school, the material, then I also highly recommend that you can start thinking about doing some of your own independent research right there about what could be a good starting point, even though yes, it will come to a formal class for that. So back to what I said, what do I mean by a failing starting point, so that it makes the whole process fail, won't get you a happy answer. So let me come up with a graph like this, with a scenario like this. So we can have something up and down, quite a few up and down, so there are a couple solutions here to that equation. And so let's say we want to approximate this one, okay? Let's say we want to approximate that one, but unfortunately you choose a starting point that happened to be right at the peak, like this, okay? Then here's what happened with the method, like with choosing a starting point like that. If your starting point is here, then first of all, what I can see is your tangent point, your tangent line. Your tangent point is right at the peak, and your tangent line is horizontal. So it won't even cross the x-axis, so we won't even be able to find the next value. So that's the one thing. So we must make sure we pick a starting point where it gives, and even though sometimes we pick a value that doesn't give a horizontal tangent line, but it might bounce into a, so see, check with this formula right here, x of n minus f at x of n over x of, f prime of x of n. We just have to always ensure this denominator here is non-zero. See, so this horizontal tangent lines means our f prime at that starting point is already a 0. We can't use a formula, so that's where it fails right there. And then this is the part where, even though you have the graph, but without too much experience, and what I really mean is without too much understanding of a higher level course, that it's hard to decide. But see, even if you chose a point that's not on the peak, but then it happens to give you a tangent lines that shoots too far away. Okay, so if x of 0 is here, if we now choose x of 0 being here, yes, it gives you a tangent line that hits the x-axis, but maybe it hits you too far. Okay, it hits you too far, and then so when it bounds onto the graph right here, and it gives you, so this is x1 tentatively, okay, but then x1 is already getting pretty far away from the root right here compared to x of 0. And then from that point on, when it bounds into the graph itself and produce for itself the tangent line is even going to make it further away. Okay? And that's what I mean by by an unsuccessful starting point. But like I said, for viewers who are currently right at the beginning calculus level, then feel free to try at your own time. After the quarter is over, after the course is over, sit there and to open up some problem and start thinking about your own starting point, and you're gonna start having fun. Okay, but to really come up with a criteria to detect a good starting point, you need to really wait into a course where you learn more advanced understanding, and there you're gonna see in the whole interval from where this crossing point is, there's an interval around that where choosing a starting point in that interval will be safe. We'll be ensuring that your solution will keep getting closer. So if you pick a starting point about here, see, then so how do I know that? I mean, it's not about the picture, but it's about you will learn techniques out there that you can pick a good starting point so that your tangent line, when it hits the graph, see, when this tangent line here and you draw another one, it's gonna keep giving you the value that's closer to the actual solution. Okay, and that's what I meant earlier by sometimes if you are not experienced enough and pick a starting point, it might fail. The process might fail. So here I can only point out a few things, but to learn on your own and how to find to learn on your own how to find a good starting point that's successful, then you need to either wait to a higher course or spend a lot of time on your own to do, think of that as your own little math project outside of the classroom. Yeah, okay, and you can be able to come up with something. All right.